after we focus in on those two examples, I need to take a step back and get even more formal, to start to move from this sort of intuitive, appealing graphical notation to a linear written notation that we can calculate with. We can actually calculate with the graphical notation, but there are some things that are not evident in the graphical notation that on purpose have been sort of suppressed so that we can kind of take the communication in bite-sized pieces. But eventually we need to get to a place where we can write things down, like we write down arithmetic puzzles or problems, and do some calculations. So I'll introduce the sort of linear algebraic notation that corresponds to the graphical notation that I introduced last time. And then after I introduce that, we'll go back and revisit our examples and expose some properties. And then finally, I want to make some comments, some philosophical comments, which I can kind of foreshadow in right now. And that is basically that, in the introduction to the series, I spoke about how it is impossible to obtain a God's eye view, a sort of global view of a system, that this never works because it doesn't scale. To require at the outset in one's approach or solution to a problem a God's eye view makes it impossible to solve problems at scale. However, what we'll see is that there is an appropriate form of God's eye view, and we'll see this absolutely clearly when we focus in on what sort of organization it requires to achieve reproduction or recursion. We'll see that there is a God's eye view in the sense that the whole is reflected in the part. So every time we look at a part of a system, in a fractal-like way, we are seeing an image of the whole. So, if we are an observer of any part of the system, we are at least capable of seeing the whole, and that is an effective God's eye view that allows us to scale. And in fact, without this property, again, you don't have systems that scale. So that kind of is the lay of the land for the next several episodes.